Hello and welcome to this next video in topic 5 on sampling distributions. Here in part 2 we're going to focus on the behavior of the sample proportion. We'll start by looking at drawing conclusions about parameters. A key idea here is to understand in general how sample statistics behave relative to the parameter that summarizes the entire population. In other words, what's the relationship between samples and proportions? When we look at the behavior of a sample proportion relative to the population proportion, this is the case where our variable is categorical. On the other hand, in a later video, when we look at the behavior of a sample mean relative to the population mean, our variable is quantitative. In this video, we'll focus on this first one, the behavior of the sample proportion. Let's start with an example. Suppose we know that 60% of all part-time college students in the United States are female. In other words, we're being given a population parameter. We're being told something about all part-time college students in the U.S. Question here is, what would we expect the behavior of sample proportions to be if we took random samples of size n equal 100? So to be clear here, what we're saying is let's take samples of size 100 and let's see what would happen if we did that many times. Now, due to sampling variability, the sample proportion will take on values that vary according to the laws of chance. One sample might have a proportion that's different than another one, and so on. In fact, they will. So because we're going to get different values for the proportions based on the sample that we take, assuming again that we take many samples, we can think of the sample proportion as behaving as a random variable. Sometimes the proportions will be larger, sometimes they'll be smaller, but in particular, if we were to look at all those proportions, we could see that it has a distribution with a center, a spread, and a shape, just like any other variable would. So our question becomes, what does that distribution look like? So let's take a look at the distribution of the sample proportions center, spread, and shape, again assuming that we take a lot of samples each of size n equal 100. First, for the center, we should expect that they will be relatively close to the proportion of p equals 0.6. Now, some might be above that, some might be below that, and a few might even be far away from 0.6, but we would expect the center to be relatively close to 0.6. In terms of spread, the sample proportions should again be close to 0.6. We should cluster around that value if we have a sample size of 100. If our sample size was smaller, let's say 10, that might not be the case because in a situation like that, one or two relatively far away proportions, so to speak, might actually affect the spread more than if we have a sample of 100. But with a sample size of 100, we expect them to be clustered around the population proportion. And finally, for the shape, we would expect that proportions close to 0.6 would be the most common, and values far away would be less likely. So again, that gives us the idea that we would have a normal distribution where many are close to the center and there's kind of a bulge in the middle, and then over at the tails you have fewer proportions close to 0.6. So our initial hunches tell us that our distribution of sample proportions should have a normal distribution with a center that's close to the population proportion and a spread, again, that tells us that most of our proportions are close to that population proportion of 0.6. So, when we talk about this distribution, let's give it a more formal name. The distribution of the values of the sample proportions, remember, since we're talking about samples here, we talk about p hat here. This is the notation we've seen before. If we do this in repeated samples, we call this the sampling distribution of p hat. So again, thinking of the sample proportions as a random variable, it has a distribution, and we call that the sampling distribution of p hat. So in this next activity, we're going to check whether our intuition about the center, spread, and shape of this sampling distribution was actually correct. So in the video that you're going to see here, the narrator is going to use simulations of multiple samples to do this for us.
In this movie, we're going to discuss the behavior of sample proportions by investigating these two questions. When we collect random samples, what patterns emerge? More specifically, what is the shape, center, and spread of the distribution of sample proportions? To investigate these questions, we're going to return to the familiar context of the previous example and look at the population of all part-time college students. We're assuming that 60% of this population is female. Now, what we're going to be investigating in this movie is what happens as we begin to take random samples from this population. I'm going to be collecting random samples of 25 students at a time. You will see the sample here, and to the right you will see the number of females out of the 25 randomly selected part-time college students. In this case, 17 out of 25 is 0.68. This is our p-hat value, our sample proportion. We will graph each p-hat above to generate a graph of the sampling distribution of sample proportions. Let's collect a second random sample and see what happens. This time we got 18 out of 25 of the students being female, which is a sample proportion of 0.72. We see that graphed here. Let's collect another random sample. We see this time we got 0.64. 16 of the 25 randomly selected students are female. We can begin to see, as we collect more random samples, that there is going to be variability, as we might expect. Each random sample will have a different proportion of females. What we're interested in is what is going to happen when we begin to collect many random samples. While we run the simulation, we're going to pause the movie and have you make some predictions. We want you to think about, if we collect many random samples, what will be the shape and center and spread of the distribution that results.
So at this point, I would definitely recommend that you pause the video and then go ahead and think about this question. What will the shape, center, and spread of this distribution look like based on what we've already said? When you're ready, go ahead and pick up the video by taking it off of pause and resuming play.
Let's see what happened. I collected over 2,000 random samples. Each sample had 25 part-time college students in it, and for each sample I calculated the proportion that were female, and I recorded that here. Did you predict correctly? What looks like happened over the long run is that many of the samples had proportions that were close to the population proportion of 0.6. We can also see that as we moved further away from 0.6, we had fewer samples with sample proportions in that range. We can get a more accurate sense of the variability in sample proportions by looking at the standard deviation. Here, the standard deviation is roughly 10%. That tells me that typical samples had proportions that fell between about 0.5 and 0.7. Here in the graph, I have marked one standard deviation below and one standard deviation above the mean of 0.6. Another thing we notice is that the shape is approximately normal. I have used a mathematical formula here to graph a normal curve on top of the sampling distribution, and we can see that the normal distribution models the sample proportions well. This is encouraging. It tells me that a normal model will be a good probability model for the sampling distribution of sample proportions. Now, in the next movie, we're going to investigate this issue of variability in sample proportions in more detail and look specifically at the impact of sample size. We'll see you then.
So as you can see, if we look at this video and what happened there, and we can ask the question, were we correct about some of our hunches earlier on, it appears that we actually were. It turns out that random samples of the same size, in the video's case n equal 25, drawn from the population will indeed have sample proportions close to p, our parameter. In other words, the distribution of sample proportions has a mean of p. Also, sample proportions are approximately normal, at least in this case. And as the narrator of the video said, that's promising because it tells us the normal distribution is a good probability model that we can use later. Now, the next question we can look at is, what variability in the sample proportions would we expect to see if the sample size is different? In particular, if the sample size was larger, let's say it moved from n equal 25 to a larger number, will the samples better approximate the population? Once again, we're going to use simulations in the movie that you're going to look at, and then tie our findings to some more formal theory.
In this movie, we will continue our discussion of the behavior of sample proportions. In particular, we're going to investigate this question: how does the size of the sample impact the spread in the sample proportions? To investigate this question, we're going to return to the familiar context of the previous movie and look at the population of all part-time college students. We will assume, as we did before, that 60% of this population is female. Now, in this movie, we're going to be comparing two different distributions of sample proportions. Both distributions will be generated by collecting thousands of random samples, but they will differ in the sample size that we use. We will return to the sampling distribution we generated in the previous movie when we collected random samples of 25 students at a time, and then we will generate a second sampling distribution using a larger sample size. We will look at samples of size 100. The question then that we are interested in is whether or not this increase in sample size will have an impact on the spread. Now, before we actually begin to collect random samples, let's remind ourselves what we observed previously. When we collected samples of 25 students at a time, we saw that the sample proportions were normally distributed and centered at 0.6. In other words, when I took all of the p-hat values collected from the thousands of samples and calculated the mean, I got 0.6, the population proportion. When I calculated the standard deviation of the p-hat values, I got about 0.1. So for samples of size 25, we saw that typical values fell between about 0.5 and 0.7 within one standard deviation of the mean. Now we're interested in what happens if we increase the sample size to 100. Will we expect to see more variability? Variability that is roughly the same, or much less variability? In particular, we're interested in finding out what happens to the standard deviation. Before I begin to collect random samples of 100 students, let me get you oriented to what I have here on the screen. Here you will see each sample and the 100 individuals in it. We'll be able to tell if they are male or female. On the right is a table that summarizes what happened in a sample. For example, here I had 67 females out of the 100 randomly selected part-time college students. That's a p-hat value of 0.67. The p-hat value is graphed above. Here is where we will generate the sampling distribution. Let's see what happens now as we collect a random sample. Here I have 100 randomly selected part-time college students. For this particular sample, I get a sample proportion of 0.65. I've graphed that above. I've now turned the animation off so that we can collect samples more quickly. What we're interested in is what is happening to the spread that we're seeing in the sample proportions. We're expecting that many of the sample proportions will be close to the population proportion of 0.6. But do we think we will see more variability, less variability, or variability that's about the same as we saw previously? We're going to pause the movie and ask you to investigate this question. What do you think will be the standard deviation of the sample proportions when the sample size is 100?
So what do you think? Is the standard deviation going to be smaller than 0.1, bigger than 0.1, or equal to 0.1. Go ahead and pause the video, think about that a little bit, and when you're ready, go ahead and hit resume.
Let's see what happened. Is your intuition correct? Here on the right, I have the sampling distribution generated from taking thousands of random samples where each sample had 100 students in it. I can see visually that there is much less variability in this sampling distribution than in the previous one. If I compare the standard deviations, I can get a better sense of what happened. When I had a sample of size 25, the standard deviation in sample proportions was about 0.1. When I increased the sample size by a factor of 4, the standard deviation decreased to about half of what it was previously. So I can conclude that larger samples do have less variability. I also notice that the mean of the sampling distribution stayed at 0.6, so the mean does not seem to be impacted by sample size. I also see that the distribution is normal for this case. Now we're going to move back into the text where we will see what advanced probability theory has to tell us about calculating the standard deviation of sample proportions. We will also find later that the distribution will not always be normal.
So as we just saw in that second video activity, when we take larger random samples, we do get better approximations for the population parameter. In fact, the sample proportions are closer to the population proportion P, and the sampling distribution for large samples has less variability. This all gets confirmed with more advanced theory that's going to tell us specifically what we can expect to be the relationship between a sample proportion and a population proportion. In the next video, we'll look at what that theory tells us, along with a couple of examples to help drive those points home.